We're asked to find the gradient vector field of f of x comma y equals x to the third, y to the fifth. So because our function is a function of two variables, the gradient vector field is going to be a two-dimensional vector field. To identify the gradient vector field, we use this notation here, and we often say del f. So the gradient vector field is equal to this two-dimensional vector field, where the x component is equal to the partial derivative of f with respect to x, and the y component is equal to the partial derivative of f with respect to y. So once we find the gradient vector field, we'll take a look at this graphically and explain what it tells us about f of x comma y. So the gradient of f, or del f, again, it's going to be a two-dimensional vector field where the x component is equal to the partial derivative of f with respect to x. So we treat y as a constant, and therefore the partial derivative with respect to x is going to be 3x squared y to the fifth. The y component is equal to the partial derivative of f with respect to y. So now we differentiate with respect to y, treating x as a constant. So the derivative is going to be 5x to the third y to the fourth. So this is the gradient vector field of our function f of x comma y. And now let's look at this graphically. The surface given by f of x comma y is graphed here in blue, and the yellow plane graphed here is parallel to the xy plane. So as we animate the yellow plane, we're going to see the corresponding level curves graphed in blue on the left, and the gradient vector field is also graphed in red. So as we animate the yellow plane, notice how the level curves on the left change. And if we pause, let's say here, if we take a look at the level curves on the left, the gradient vectors are going to be orthogonal or perpendicular to the level curves. So that's one property of the gradient vector field of a function. And the other property is if we were to find the gradient vector at any point along the surface, it would point in the direction of maximum increase or steepest descent. So for example, if we consider this point here, let's say it corresponds to this point on the surface, this gradient vector tells us in what direction to walk or move so that the function would increase the most or the direction of steepest descent. If we moved in the opposite direction of the gradient vector, it would be the direction of maximum decrease or steepest descent. And that should make sense because again, if the corresponding point was here, the gradient vector is telling us to walk in this direction, which should be the direction of steepest ascent or maximum increase. Notice how we'd be going uphill very quickly. If we moved in the opposite direction, we'd be going downhill very quickly, which would be the direction of steepest descent or the direction of maximum decrease. I hope you found this helpful.